Evaluation of a mass moment of inertia of an arbitrarily shaped body, that is, without any symmetry planes, requires a full three-dimensional calculation. When using integration, we'll restrict ourselves to simpler bodies having at least two symmetry planes so that we can reduce the calculation to a one-dimensional integral. In figure B of this slide, we have an object of revolution about the y-axis. We'll restrict ourselves to describing it in terms of a generating surface in the xy plane. The differential element is a cylindrical shell of radius ry tilde equals x, height h of x, and infinitesimal volume dv equals the circumference 2 pi ry tilde, or 2 pi x, times its thickness dx times its height h of x. Every material point in the shell is at the same distance ry tilde equals x from the y-axis. So in this case, we have Iy is an integral or a sum over x, ry tilde squared, which is x squared, times the density times the volume, h is a function of x, 2 pi x dx. An alternative one-dimensional approach is to integrate over y. In figure C, we are using a disk element and summing the disk elements of variable radius axially. We will show shortly that the mass moment of a disk about its polar axis, in this case the y-axis, is 1/2 mr squared, where m is the mass of the disk and r is its outer radius. In the present case, we are summing the contributions of infinitesimal disks as diy equals 1/2 dm times the radius of the disk squared. As in the case of figure B, we have an object of revolution and we're confining ourselves to a generating surface in the xy plane, but now we're summing over y, so here we suppose that the radius of the disk, which is x, can be written as a function of y, and we have 1/2, the incremental mass is the mass density rho, times the area of the disk, which is pi x squared, but x is a function of y, times the disk thickness dy, so all of that in parentheses is dm, times the radius of the disk, which is x as a known function of y, squared. More generally, we'll show that for the situation in figure D, where we have an object that's symmetric about the xz and yz planes, an increment of mass moment can be expressed as Iy equals an integral diy, where diy can be expressed as some function of y dy. The functional form of f of y will involve applying the parallel axis theorem to differential elements, as we'll show in examples 3 and 5. The point of this first example is to demonstrate that for thin plates, we can establish a relationship between our area moments of inertia and mass moments of inertia. For reference, the area moments for this geometry and set of axes is given at the top of this slide. Now consider the definition of the mass moment about the z-axis. The perpendicular distance between the z-axis and a mass increment dm is rz tilde squared equals x squared plus y squared. But the x-coordinate is restricted to an interval between minus t over 2 and plus t over 2. If the plate is thin, then x squared is much less than y squared for all but a narrow band of material points near the z-axis. For this reason, the integral is well approximated as the integral of y squared dm. If the plate is thin, we can write dm, which is rho dv, as mass density rho times plate thickness t times dA. If the thickness is uniform and the density is constant, we can pull the rho t product out of the integral and write the mass moment is product of density and thickness times the integral of y squared dA, but the integral of y squared dA is exactly equal to the area moment of inertia about the z-axis. This gives us the critical relationship that the mass moment for a thin plate is related to the area moment by this product of density and thickness. And we have similar relationships between the mass and area moments about the other axes. These results will be very important to us in constructing generating elements for the evaluation of mass moments using integration. Let's go back one slide and see how this works. We had previously stated without proof that an increment of polar mass moment could be written as diy equals 1/2 dm times the radius of the disk squared, which gave us this result. Our thin plate results can also be used to generate this same expression. Now the plate thickness becomes infinitesimal, so T goes to dy, and the mass moment goes to an infinitesimal mass moment diy. So now we have an increment of mass moment equals mass density times infinitesimal thickness times area moment about the y-axis. But we had previously shown that for a circle, this was pi over 2 times the radius of the circle to the fourth. In this case, r is just our x of y, but this is exactly the same as what we have here. We'll return to this to see how to generate expressions for mass moments of axisymmetric solids in examples 3 and 5. This example asks us to show that the mass moment of inertia of a homogeneous thin disk with uniform thickness about its axis of revolution is Iz equals 1/2 mr squared, where m is the mass of the disk and r is its outer radius. It actually turns out that Iz is represented by this expression no matter how large or small the uniform thickness T is. The thickness could be on the order of or much larger than the radius, and we would still get Iz equals 1/2 mr squared. To show this, we'll use a differential cylindrical shell element as in figure B of slide 8. In this case, Iy becomes Iz, h becomes t, and more importantly, t is constant and so not a function of x. In this case, our result looks like this. We're integrating from 0 to r x squared density times thickness times 2 pi x dx. We can pull out the 2 pi rho t, and we're left with an integral from 0 to r x cubed dx. The integral simply becomes 1/4 x to the fourth between these limits, gives us pi over 2 density times thickness times r to the fourth. Now we could actually leave our result this way, but it's traditional to recombine terms so that we get something that's clearly defined as the mass of the object in the expression. And we could write the mass as density times volume for a cylinder, whether it's a disk or a larger cylinder. This is just going to be pi r squared times the thickness. So we'll group terms, and that gives us 1/2 mr squared. Here in example 3, we have a more complicated problem. We have a spinner for an airplane propeller, It is solid with uniform density rho and is formed by rotating a generating curve about the x-axis. We want to determine the mass moments Ix and Iy and express the results in terms of the total mass m of the spinner. As shown in slide 12, there are two natural choices for volume elements, and in this case I'll choose the circular disk element, which means I'll be integrating over x. If you like, you can try to reproduce the results later with the thin cylindrical shell volume element and integrals over y. Because this is a non-standard object of revolution, and we don't have its volume tabulated in the back of the book, we should first verify the expression for the mass. We can do this by summing disk elements over the length to get the volume. That is, we could write the volume as a sum over the length from 0 to L in x. The local radius of the disk can be described as a function of x as r equals y of x. And the volume increment is the area of that disk, which is pi r squared. Pi y is a function of x squared, times the thickness dx. We can rearrange the result for the generating expression to write this as y squared equals r squared times the quantity 1 minus x squared over L squared dx. We can pull the pi r squared out, and we're left with the integral, with the resulting integral, which gives us x minus x cubed over 3L squared, evaluated between these limits, and which ultimately gives us 2/3 L, so this is 2/3 pi r squared L, and the mass of our object can then be written as rho times 2/3 pi r squared L. Now we want to evaluate the mass moments Ix and Iy, and what will be critical here is understanding the relationship between a local centroidal xyz set of axes for the differential element and the x, y, and z axes in the problem figure. So let's keep in mind here that we have local axes. Here's x prime, y prime, and z prime that go with the differential element. In particular, note that x and x prime are coincident, which means we don't have a parallel axis offset, but y prime and y are not coincident, which means we will have a parallel axis offset. Our differential contribution to mass moment about the x-axis will then be the same as that differential contribution about the local x prime axis, and we know that that's 1/2 the differential mass times the radius squared, so that's 1/2 mass density pi r squared dx. There's our differential mass dm is here, times radius squared, or Ix will be the integral from 0 to L, 1/2 rho times pi y of x raised to the 4th power dx. This result will look like this. We'll pull the mass density and pi over 2 out in front. We're integrating from 0 to L. We can think of that y to the 4th as y squared quantity squared, which gives us, in the integrand, r to the 4th times the quantity 1 minus x squared over L squared quantity squared dx. We can then expand that integrand to get rho pi over 2. We'll pull the r to the 4th out again, and we're integrating from 0 to L, 1 minus 2 x squared over L squared plus x to the fourth over L to the fourth dx. Integrating that, we get x minus 2/3 x cubed over L squared plus 1/5 x to the fifth over L to the fourth, and we're evaluating that between the limits of 0 and L. And we're going to get out of this a quantity L times 1 minus 2/3 plus 1/5, and we can put all that over one denominator and get 8/15 L. So that gives us Ix equals rho pi over 2 r to the fourth times 8/15 L, which ends up being 4/15 rho pi r to the fourth L. Now, once again, what we want to do with this is collect some terms that we can clearly identify as the mass. And so if we do that, let's write this as 2/3 rho pi r squared L. That's the mass. And then in order to generate our expression Ix equals 4/15 rho pi r to the fourth L, we need to multiply that by 2/5 r squared, which gives us a mass moment about the x-axis of 2/5 mr squared. The calculation of Iy is not as straightforward because the center of mass y prime axis for the differential disk element is not coincident with the y-axis of the problem coordinate system. So let's go back up here for just a second. And we'll make a note here that all the material points in the differential disk element are at the same distance x from the y-axis. So what we're going to have is a differential contribution about the y-axis is a differential contribution about the centroidal y-axis of the disk element plus the parallel axis offset. There's a distance x between the two axes squared dm. Also remember that because we can write these mass moments as a density times a thickness times the area moment, and for a circular disk, the area moment about the planar axes is 1/2 the moment about the polar axes, we could write this as 1/2 dix prime plus x squared dm. And this relationship diy prime equals 1/2 dix prime is particular just to this disk element. So this is going to be 1/2 times our previous expression. And remember that dix prime was rho dx, rho times thickness, times the area moment, which was pi over 2 radius to the fourth. Plus we have x squared, and the mass increment is density times cross-sectional area of the disk times its thickness dx. So our expression for the mass moment about the y-axis has these two terms, and the first one looks almost identical to what we had for the mass moment about the x-axis. It's just that we have a pi over 4 here now instead of a pi over 2. And our second term looks like this. Now we actually already know what this is going to look like. This is just going to be 1/2 the value that we had for Ix, so I'll just write down that this is 2/15 rho pi r4 L, and we'll concentrate on just the second term here. So that term, we can pull out the rho pi r squared, and we're integrating from 0 to L x squared minus x to the 4th over L squared dx. That integrates to 1/3 x cubed minus x to the 5th over 5L squared, evaluated between 0 and L, and we end up with rho pi r squared L cubed times 1/3 minus 1/5, which is 2/15 rho pi r squared L cubed. Our expression for Iy then, because we have a common 2/15, we could write it this way. We have some common terms here, times the quantity r squared plus L squared. And then once again, we'll collect terms that can be clearly identified as the mass. And we have to multiply that by 1/5 to get our 2/15. And that gives us our final result, that Iy is 1/5 of the mass times the quantity r squared plus L squared.